Captain Calculus will now do exponents. It should be crazy.
This is a new topic in algebra, and I'm just going to do a really long video. I just feel like doing a really long video. We'll see how it goes. You should already be familiar with these two rules. We did those way back in the day. So if you remember, if we have x squared times x to the power of 4, the answer is going to be x2 plus 4, which is x to the power of 6. And the sort of little proof that I did was x squared is x times x times x times x times x times x equals x to the power of 1, 2, 3, 4, 5, 6. Okay, so far so good. But what if the variable is in the indices, is in the exponent, as in that? So now x is 2 to the power of x, and we want to know what x is. Okay. We'll just do some terminology before we proceed. So I'm going to call that the exponent from here on in. It's sometimes called the power, the superscript sometimes, meaning it's up here, and the indice. But I'm going to call it exponent. The number down the bottom here, I'm going to call the base. So this would be base 2 raised to the x power, the x exponent. Okay, so far so good. What do I mean when I use the rule if a to the m equals a to the power of n, then m must equal n. Let's do an example. So 2 to the power of 3 equals 2 to the power of what? And I want you to solve for x. Well, there's only one possible way that this can be true, and that is if 3 equals x, or if we want to rearrange it, if x equals 3. So for our sake for now, we're going to presume that the number up here is a nice clean number. We're not going to be working with 2 to the power of 3.2168 or something like that. We're only going to be talking about really whole numbers, integers, things like that. Okay, so far so good. The trick is always, well, almost always, try to make the base the same. Okay, so if I have 3 to the power of x equals 9. What's the base of this one? Well, the base there is 3. The exponent is x. Okay. This one here, what's the base and what's the exponent? Well, the base is 9. The exponent is actually 1. But we can't say that x equals 1 because they don't have the same base. So we have to convert this one to base 3. So we're going to do a sort of side equation. 3 to the power of what equals 9? Well, you should know that 3 squared, 3 times 3, is 9. And we're only going to really use the positive integer value. Note that negative 3 squared can also equal 9. So therefore, 3 to the power of x equals 9, which also equals 3 to the power of 2. And now we do have the situation up here where we have the same base and only the exponents are different, and when the base is the same, the exponents must be the same as well. So therefore 3 to the power of x equals 3 squared. It follows that x must equal 2. And let's do a little test. So if we get our original equation 3 and we put a 2 there, does that equal 9? Yeah, it does. It equals 9. It's just worth doing maybe a couple of examples of this. So if I say that 6 to the power of x equals 36 is a pretty easy one. This one, obviously, we want to convert that to base 6. So we want to say x to the power of what equals 36? Well, x squared is 36. So 6 to the power of x equals 36, which equals 6 to the power of 2. Therefore, x must equal 2. Our rule here does all of the work. So it really behooves you to sort of have a table and to sort of know what the common powers are. And I've done one here. So here I have a number. 2 to the power of 0 is obviously 1. Anything to the power of 0 except for 0 is 1. This one here means 2 to the power of 1 is 2. This one here is, well, I've changed them around. This one should be 2. It's better. This one here is 2 to the power of 3 is 8. Notice they double every time we go up, and here I've done the negative values, which we'll get to later. 3 to the power of 0 is 1, of course. 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. 3 to the power of 4 is 81, and so on and so on. And I've done them up to 7 to the power of 6, which is what, 117,649. You don't have to memorize these. Maybe if you're going to memorize anything, you know, the 2s and the 3s. If they need any more, you can always work it out in your calculator. But this table is really, really handy, and it's one that we'll be coming back to quite a lot. An example would be something like this. Say I have 5 to the power of x, and that equals 3,125. What would we do here? Well, probably you go to your calculator, to be perfectly honest. But let's not use the calculator. I'm going to say this is actually really, really easy. So I'm going to say 3,125 is equal to 5 to the power of what? What would need to go up here to equal 3,125? And I'm going to bring up my table here. and I find the 5's, and I go across. So 5 to the power of 5 equals 3,125. So 5 to the power of 5 is 3125. So therefore we know that 5 to the power of x equals 3,125, and we know that 3,125 is 5 to the power of 5. So therefore 5 to the power of x must also equal 5 to the power of 5, and the bases are the same, so therefore x must equal 5. 5 to the power of 5 is 3125. So far so good. Let's look at a slightly different example. So if I said 6 to the power of x plus 12 equals 6. Okay, can we use that rule? The answer is yeah, we can, but we don't quite have all the information that we need. Do these have the same base? Yeah, they do. The base is the same. What's the exponent that's up here? The 6 is just 6 to the power of 1. Remember our rule from way back as well. These have the same base, so therefore x plus 12 must equal 1. So therefore we take 12 away from both sides. X must equal negative 11. Let's test it out. X to the power of negative 11 plus 12 equals, 6 to the power of negative 11 plus 12 equals 6 to the power of 1, and that is 6. That's kind of a mini proof. That's how that works. Conversely, remember this rule, a to the power of m, where a is any number and m is any number, I suppose except for 0, divided by a to the power of n, it's going to be equal to am minus n. So an example of that would be 6 to the power of 5 divided by 6 to the power of 2 is going to be 6 to the power of 5 minus 2, and hopefully you don't need a calculator for that, is 6 to the power of 3, and you may need a calculator for that, but let's go to our table. 6 to the power of 3, we find 6 to the power of 3 is 216. Moving along, let's do some more examples. So we want to solve for x, so we want x equals some number. At the end, 3 to the power of x equals 81. Okay, we need to convert this into base 3. So 81 is 3 to the power of what? So for this we would go to our tables. 3 to the power of 4 is 81. Three to the power of 4 is 81. So that tells us that 3 to the power of x equals 81 equals, we'll cut and paste that, 3 to the power of 4th. So 3 to the power of x is equal to 3 to the power of 4ths. So x equals 4. Pretty standard. Alright, for this one, so we want to find x plus 1 equals 16. So we need to convert this one into base 2.
And I know that, let's kind of go through the bases of 2. Base to the power of 0 is 1. Base to the power of 1 is 2. Base to the power of 2 to the power of 2 is 4. 2 to the power of 3 is 8. And 2 to the power of 4 is 16. Notice they double each time. So therefore, 2 to the power of x plus 1 equals 2 to the power of 4. And we know from our rule, therefore, that x plus 1 equals 4, and suddenly everything is down in its normal script. We need to get rid of this positive 1, so we're going to take 1 away from both sides. So x is going to be equal to 3. Okay, so an interesting one. 5 to the power of what is 1 over 25. Now remember that a to the power of minus m is equal to 1 over a to the m. So in other words, 5 to the x is equal to 1 over 5 to something. So 5 to the power of what is 25? Well, 5 squared is 25. So using this rule here, 5 to the power of x equals 1 over 25 is equal to 5 to the power of negative 2. So 5 to the power of x equals 5 to the power of negative 2. X therefore equals negative 2. And let's sort of test it out. Let's bring up a calculator. So 5 to the power of negative 2 is 0.04. Convert that into a decimal, into a proper fraction. That's 1 over 25. Alright. Another one. Again, we're wanting to solve for x. So x, we have this 4 to the power of 2x's. 4 is the base, so we need to convert the 64 into a base 4. So 64, we would go into our tables. So here in this column here we have our base 4s. So base 4 to the power of 4 is base 4 to the power of 3 is 64. So prove it in here. So 4 times 4 times 4, that's 64. So therefore 4 to the power of 2x equals 4 to the power of 3. So therefore 2x equals 3. And now we want to divide both sides by 2. We're going to go to 1. And our answer is 3 over 2. So in other words, let's test it out. Is 4 to the power of 2 times 3 over 2. Does that equal 64? Let's grab the calculator. 4 to the power, I'm going to put in brackets, times 1.5, 3 over 2 is 1.5. Yep, 64. In this question, we're given a real life word problem involving growth, exponential growth. So a population of bacteria doubles every hour. If there are 100 bacteria now, how many will there be in 3 hours? And this isn't just a hypothetical question. Doubling every hour is pretty long for bacteria, as I'll show you now.
Bacteria reproduce very simply and rapidly by doubling their contents and splitting in two. Just one bacterium, dividing every 20 minutes, could produce nearly 5,000 billion bacteria in one day.
So let's look at our example. We're told that it doubles every hour. So it's 2 times what it was the hour before, every hour. I'm going to presume maybe it's on the hour. We start with 100 bacteria and we're asked how many bacteria will we have after 3 hours. So let's use our let statement. So the bacteria after 3 hours is going to be, well, we start with 100. After 1 hour, we're going to double it. And then we're going to double it again.
And then we're going to double it again. So 100 times 2 times 2 times 2 is 800. 800 bacteria. Bacteria. One cell would be a bacterium. Okay, well that's fine if we only have three time limits. But what if we're trying to find the amount of bacteria after 12 hours? Or after 24 hours? Well, I don't know about you, but I'm not gonna hit times 2 times 2 times 2 times 2 times 2 24 times. So if we can find a general statement, the amount of bacteria after some time limit, where number of bacteria is a function of the time. Well, notice here it's 2 times 2 times 2, which is 2 to the power of 3 by definition. So we can say that the amount of bacteria at some time is going to be equal to the amount we started with times 2 to the power of the number of hours that have gone by. So let's work out what it would be for bacteria 12 using that formula. So that's going to be 100 bacteria that we start with times 2 to the power of 12, and I have no idea what 2 to the power of 12 is, so let's grab the calculator. Okay, so 100 times 2 to the power of 12 is 409,600. A lot. But, I mean, not a lot for bacteria. What would it be after 24 hours? So it would be 100 times 2 to the power of 24, and this is going to be a huge number. A lot. A big number. In the exam, by the way, if they ask you for the number, don't just say a big number. You'll get no marks. In accounting, there is a concept called depreciation. And what it means is that an asset will lose value over time. So if you buy a car, as soon as you drive it off the lot, it loses, I think, a third of its value. And then the older the car gets, the less the car is worth until you may have to write it off. So this is actually an exponential problem. So we're given the problem that a car loses 20% every year. If it's worth $10,000 now, what will it be worth after 1 year? Well, if it loses 20%, that means it keeps 80%. So just explain that. So it loses 20% is the same thing as it keeps 80%. So after 1 year, the value will be 0.8 times the original value. Okay, so it's a really important way to work it out. We have to work out the percentages first, so we have to know that first. Okay, well, let's work it out. So let's say the value after 1 year is going to be equal to the original amount times 0.8, which is going to be 8,000. Okay, let's take it a bit further. What about after 3 years? Well, after 3 years, it's going to be $10,000 what we started with. It loses 20% after the first year, and then it loses another 20% the second year, and then it loses another 20% the third year. And if you notice, that is really similar to the last one, but instead of exponential growth, it's now exponential decay. It's reducing, which is the same as 0.8 to the power of 3. So we can work out a kind of general statement. The value of this thing over time is the original price, original value, times 0.8 to the power of the number of years. So what would it be after 3 years? Well, for that we would use the calculator again. If it comes up, there it is. So the calculator is 10,000 times 0.8 to the power of 3, $5,120. A short side note on decay. If you recognize this is our $100 note. Ernest Rutherford, Lord Rutherford of Nelson, there is his full title. Here is his Nobel Prize from 1908. He got given his Nobel Prize. The thing that he got given his Nobel Prize for is shown here in detail. So we have an exponential decay model. And what he found was that radioactive materials decay at a set rate. It's not a straight line. It halves in radioactivity or radioactive emission every half what's called a half-life. So if there is 100% of its emission here, after one time interval, it'll be down 50%, then another 50%, then another 50%, then another 50%. It's exactly the same, quite exactly the same, as our example here with this $100 note, where things decay 20%. Here they're going to decay 50%. They half and half and half. It's why radiation, when something becomes radioactive, it's most dangerous when it first decays because it's releasing as much radiation as it can, and after a set period of time it'll halve and halve and halve. If you have a look at that graph, here is the actual graph itself. So if you notice that the equation is 0.5 to the power of x, and it halves every time limit. So here the time is 0, so 100% of what is there, and then after one cycle, one time interval, it's down to 50%. After 2 time cycles, it's down to 25%. This is a very, very common decay. A lot of things in nature, and especially chemistry, rely on a half-life. So you can calculate how much of a substance there will be present given a half-life. With that decay model, let's look at another example. This is from the field of pharmacokinetics, which is the study of how quickly medicine leaves the body. It's the mathematics of chemistry, biological chemistry. So we're told that the medicine dose halves every 6 hours. The initial dose is 80 milligrams. How much will remain after 12 hours? Okay, well, if it halves every 6 hours, so let's say the amount of medicine after a certain amount of time is equal to the initial amount. So we start with that, and then we multiply it by half times the number of time intervals. But watch out, there is a trap. It would be really, really tempting to say, okay, well, in this case it's going to be equal to 80, and it's going to half, well, it's 12 hours, so there must be a 12 up here, and that would be wrong. It might be 12 hours, but we're not talking about hours. In this case, we're talking about 6-hour lots. So in 12 hours, the amount of medicine in the bloodstream would half twice. After 6 hours it halves, and then after the next 6 hours it halves again. So the amount after 12 hours would be equal to the initial amount half to the power of 2. So really, saying half hours there, we would say 2 half-lives. And let's work it out. So we started at 80, and we halve it, and then halve it again, so we halve it twice, which is the same as quartering it. But let's grab the calculator just to make doubly sure. $80 times, and I'm going to have half to the power of 2 is 20. Same as quartering it. What would it be after 3 days? Well, first off, we have to work out how many 6 hours are in 3 days. So 3 days times 24 hours is 72 hours, and 72 hours divided by 6-hour lots is 12. And it's going to be a really, really, really small number, I bet. So it's going to be the initial amount times a half to the power of 12. And I'm going to grab the calculator. We're going to need to use the calculator for this. So 80 times half to the power of 12, 5 over 256, which is 0.0195 milligrams of the medicine in the bloodstream. So we would probably switch from milligrams to micrograms in that case. So it would be 19 micrograms in that case. Very, very, very small amount. Well, depending on what type of medicine it is. A really common question involves what's called compound interest. Compound interest is when you get interest on interest. So in this question here, we say we start off with $500. It increases 10% annually for 2 years. So in this case, it's compounded annually, so it's already in the same time scale that we need. It's not like the last question. T is going to be equal to 2 in this case. Well, let's have a look at how much this is worth. So I'm going to say I'm going to let V, and I'm going to say let V be the value at time t. I might just put that in. Okay. And we know that the value after 1 year is going to be $500 times, now if we increase something by 10%, it means it's the same as increasing it by 1.1. Remember, 10% is 0.1, and if we increase it by 10%, we increase it by the amount that we've got plus another 0.1. So that would be $550. And then after 2 years, it's going to be 500 times 1.1 times 1.1 again, and it's the same thing with exponential growth. This is the same thing as 1.1 to the power of 2. So our general formula is going to be the value of something after t number of years is going to be $500 times 1.1 to the power of t. And this is a really, really important equation. It comes back again and again and again, and it's worth sort of looking at. So Vt is the initial value times 1 plus the rate, and the rate always has to be as a decimal, to the power of the number of time periods. So what is this? Well, let's grab the calculator again. So we have $500 times, in brackets, 1.1 to the power of 2, and we get to $605. So notice what that means. It means that some of the $50 that we earn in the first year, that itself is earned another $5. It's the kind of powerful value of compounding interest. I think Einstein said, and may not have said it, he's supposedly said a lot of things. He said he doesn't necessarily believe in the laws of physics, but he does believe in the law of compounding interest. Let's have a look. What would it be after 12 years? Well, it's going to be $500 times 1.1 to the power of 12. And it's going to be interesting to see how much it is. So I'm going to clear that. $500, 1.1 to the power of 12 is $1,569. And 21 cents, which is amazing because we've more than tripled our initial investment. And on that note, let's end exponents. There'll be a little bit of exponents still to go when we do graphing next, but that's pretty much the basics done.
Balls, we finally beat exponents.